I want to remind you some unique problems. So if you have a shaft problem, so basically you have a cylinder and the shaft could be carrying some kind of moment and also some kind of twist. And maybe the teeth talk is like this, right? So because of this bending, if I bend it in a different direction, so I bend it down, then at the top, at the very top, if you view this material, if your eyeball is right here, and if you are viewing this very top element, and this is what you see from the top, you will be stretched left and right? So the stress due to that bending equals to 32m over pi d cubed. So if the diameter is d, and due to the twisting, you will have shear stress. And if you view from the top, this particular position is being twisted like this. So the shearing force goes down on the right and goes up from the left. And usually it's a coupled shearing forces. So over here you will have the opposite twisting shearing stresses on the other direction, so they balance out. So all these equals to tau, and it equals to 16t over pi d cubed. Right. So for shaft problem, for many times you will see this force diagram, and if you draw a Mohr circle, right, this is your stress, this is your shear, and if the counterclockwise is positive, and if you stay right here, let's say this is point A, and it has a positive stress, so here is your positive stress, and then you have a negative shear stress, so right here, negative tau, and that would be your point A right here, right? And if you go up to this point B, and there is zero positive, zero stress, zero normal stress, and there is a counterclockwise tau, so there would be a positive tau right here. So this is point B. So at the end, this is the center point, right? And you will be drawing this Mohr circle like this. And right here you can see this is half of your stress, and this is tau. So the radius right here, the radius equals to tau max, of course, because this is where you have the maximum shear stress, would be square root of sigma squared over 4 plus tau squared, and taking a square root. So this equation can be seen at many places from previous textbook. In this lecture, we see this many times. And because for mechanical design, we care about the shape. Most of the mechanical components that is carrying loads, sometimes fluctuating loads, are on the shape. The loads fluctuate due to the rotation of the shaft most of the time. So that's why we see this equation very often. Uh, so once you have this, remember this is also a plane stress plot. Sorry, it's from Ministry of Education. So right here, this equation is this simple because it's a plane stress problem. So if we are dealing with some other geometry and the stress condition is more complex, and if the force diagram is more three-dimensional, then the equation won't be this simple. So this equation is only for this low condition, and also if we have the equations for the shaft plug it in, then we do have a more a bigger equation like this, 32m over pi d cube squared over 4 plus 16t over pi d cube squared. And this is the maximum shear stress. For maximum shear stress model, if you use this model, this value has to be smaller than the yielding strength divided by 2, half of the yielding strength. And if you consider safety factor, then you have to multiply an n on the bottom of right hand side. Okay, so that's basically what I'm showing right here. Okay, this is a shape problem. So it's a plane stress under pure bending and pure twisting. Then you have this force diagram. You can compute for the maximum shear stress, and the model looks like that. Okay, and for this particular problem, if you look at the principal stresses, this is S1 and S2. So right there, S1 equals to the center point, basically half of the stress plus the radius. The radius is basically this. Right? This is the first principal stress. And the second principal stress is this, minus the radius. Okay? Now, if we apply maximum distortion energy model, so the model tells us we will have this volumetric stress, and it's gonna be S1 squared plus S2 squared minus S1 times S2. And that value has to be smaller than the yield strength over the safety factor. Right? This guy is volumetric stress. So for plane plane stress problems. Okay. Now we're going to try to plug in those values into this equation. And how do we have these? This is only for this particular Moore circle. So only for this particular low condition. Only for, not only, but this condition is commonly seen in a chef problem. Okay? So now let's try to plug in. When you do that, you do have square root of sigma 4 plus 2 times you do have 2 of these and also 2 of those. Sigma over 4 plus sigma 2. And you do have 2 times this times the square root and minus 2 times this and the square root, so they balance out. And also minus S1 times S2. So this times that gives you sigma squared over 4. These two multiply and these two multiply, which is going to be minus sigma squared over 4 plus tau. Okay, and the cross multiplying balance out. Okay, so this big equation, this is what it looks like after you plug in, and you can see many terms will balance out. This one, so 2 times this guy minus 1 times that guy, and there's 2 times of this plus another one right there. So you can already have this is a quarter of it. This is like a half of it, and this is another quarter of it. So in total, sigma squared, right? And then you have 2 times of tau squared and the 1 time of tau squared plus 3 times of tau squared. And this has to be smaller than sigma y over n. Okay? And what's interesting is that for this particular equation, we know this has to be smaller than sigma y over 2n. If we multiply 2 on both sides, at the end you will have sigma squared plus 4 times tau squared smaller than sigma y over n. So did you see very similar terms here and there? If you use maximum shear stress model for this particular problem, the coefficient right here is 4 in front of the tau squared. But if you use maximum distortion energy model, the coefficient right here is 3. It's very slight difference. Okay? So that's why sometimes for design problems, you sometimes see this, sometimes you see this. Then you question yourself, this is 3 or 4. It's basically coming from 2 different models. And they have 2 different conservative levels. Okay? So if you plug in the sigma and tau into that equation, very similar form you will get, but the coefficient is slightly different. Okay? And of course, you can do the same thing for maximum strain energy model, and you will have a 2 times mu coefficient right there. So which means at the end you will have some of the terms inside the equation with Poisson's ratio. But what would be more interesting is just to compare these two because they are looking so similar to each other. Okay, so I just want to use this opportunity to remind you the design equation. Uh, those design equations are so commonly seen. Okay. Let's take this particular one as an example. So, and let me remind you what each term represents in a design problem. So, moment uh, and torque, they are like external forces. So, you're designing for certain level of external forces. You cannot carry super large force. Okay? And D would be geometry. You can have lighter shaft when you reduce the diameter. But if you reduce too much, this structure will become too weak. You can have stronger ones when you make it thicker, but it's gonna be very heavy. In this design equation, there's no rules about the weight. So usually the weight is a design objective. You want the weight to be lower because weight relates to cost and energy consumption. So that would be some other uh, criteria that you are looking for, but that is not involved, not directly involved in the design equation. The design equation is purely about mechanics and safety level. And key parameter about geometry is included in the design equation. And that geometrical information will be related to the cost, some other things that you are worrying about. And the yield strength basically is about the material you choose. And safety factor basically is about safety level. And it's basically related to reliability. So again, another time of reminding you what design equation is about. It's the relationship between what kind of material you use, what geometry you're designing for your component, and how much loads you're carrying. And with all these combination, how much safe level you can have. And when the safe level is equals to 1, you are designing for yielding. It's about to yield. But if you have safety level larger than 1, then you have some safety margin. Okay? So next, when is the exam? Next week? Yeah, you are going to have an exam. That's why I remind you these. Today is October 1st, right? So next week, Dr. Patel will do some exercise. So he will be solving problems. Today I just remind you what are the important equations. And next Wednesday, you will have exam. This is very important. The equation you will be using. And in the problem, okay, let me remind you again how the problem could be looking like. Okay, so we do have design equations like these. Okay, like this one is uh, the maximum strain energy model. Right? This is a shear stress model. So I can give you a problem like okay, something is carrying this load, some with some values, and maybe some shear, right? And what? And I will be asking you. I may tell you what are the key things. I may tell you no information. Right? I can tell you the yielding strength, and I can fool you by telling you ultimate tensile strength. So I can give you some number you don't need to use. And I can also give you Poisson's ratio. You may only use it for maximum strain energy model. And I can tell you the diameter of the shaft. But when I make a drawing like this, I may not, it's not necessarily for a shaft. So it depends on whether I would like to say it's actually a shaft. So another way to give the problem is I give you a drawing of a shaft and tell you it's carrying some kind of loads and indicating certain point right there and ask you to make the load diagram by yourself. So those are the possible problems I could give you. So if I make a drawing right here, usually I don't tell you dimension, right? But if I give you a drawing like this directly, there's no drawing about the shaft. So I may not give you D. If I don't give you D, that means I'm not asking you to plug in 32M over pi d cubed and 16T over pi d cubed. So it really depends on how much I would like to ask you to get together inside the equations. And usually with all these known information, what are you solving for? Safety valve. If you have stresses, you have material property, these are material properties, right? And this is about dimension. And these are loads. Then you can solve for safety. So this is one way of having a problem. Or I can make switches. I can say, okay, now we know I give you material property, and I give you a desired safety level. I want you to design for a certain level of safety, and I want you to solve for maybe for diameter. So basically same equation, but different unknown. Okay. So when you solve for these, be very careful about the inequality sign. Because if you are solving for safety level, like this particular equation, at the end, your safety level is smaller than your yield strength over your von Mises stress, right? I just write down something. Right? So you can say the maximum safety level this material will be equals to certain this number, because at the end you have n smaller than certain number. So let's say you solve your solution give you something like this, 1.2. Then you can say, okay, the maximum safety level is 1.2. And on the other hand, if you are solving for something else, like what's the best material I should use? So maybe a problem is like this, a different problem. Known geometry, known safety level, and maybe all the stresses and all the stresses, but solve for what? Solve for material property. So when you are solving for this, what's gonna how the equation is gonna look like? It will be yielding strength has to be larger than n times the permissive stress. So this tells us you need to pick a material that has a yielding strength larger than certain level. So I want you to be able to describe what the design is looking for. And sometimes students just solve the problem with equal sign. It's different. The design equation has inequality sign. It has a sometimes larger than, sometimes smaller than. It's not equal. You are not designed for the exact moment which your material is about to fail. You are designed for a safe region. So the inequality sign represents a range of possible design parameters. Okay, so I want you to solve with your inequality signs. Okay? Do you have questions? Uh, this semester, the progress of the lecture is quite slow compared to the past. Are you guys okay if the progress is slow? No one mind. Or do you want them to be faster? Okay. Uh, so for static loading, basically all I'm going to cover are just three different equations: maximum shear stress, maximum strain energy, and maximum distortion energy. That's all. Actually, I'm done with the lecture for this particular part. And since we still have some time, I would like to maybe talk a little bit about fluctuating loads. Or do you want to just wait until the next time? Oh, maybe I can kind of ah, I can share some of the knowledge that you will see in the future, but it's quite related to what we learn right now. It's about gears. Since we don't have too much time today, let me just show you what's happening about the gears. So when we design for gear, in other courses, you uh, for the gear problem, uh, we care about how much energy can be transferred from one gear to another. So if I have a motor attached to a first gear, which is gonna be rotating in certain RPM, you can compute for the rotational speed of the some other connecting gears, right? And also some positioning of the gears if you have a quite complex gear system. So that's what other lectures is about. For example, in design of mechanism or kinematics, when people talk about gears, they usually care about kinematics, not the uh, stress analysis. In most of the lecture you took in the past, nobody talk about the stress inside the gear. But what this course is about is to let you know there will be stress inside the gear and gear can fail. And I'm going to show you how, how, how do you design for gear, but not for the selection of parameters. In this course, we care about uh, the stress distribution inside the gear after you already pick up proper parameters for the gear. So I need to find the right slide. This particular one. So this is very interesting. So this is a gear. This is a one tooth of the spur gear. Okay, here we go. So how do you study for the stress inside the tooth? Basically, the tooth has a very curvy geometry. It's not easy to study for. There's no general equation to study for the stress inside the tooth. So what happened was there's a research area and they define so-called the Lewis factor. Why is so-called the Lewis factor? So I am the kind of professor who never study for the history. So I never care who is Lewis. I'm that kind of professor. I only like to solve math problems. But I know some professors who may be more interested about all kinds of historical stories about engineering development and so on. So maybe some other professor who know who is Lewis. But for me, it's just a factor under the name of Lewis. So what is this Lewis factor is about? It's so let's take a look at how it is defined. So there is one parameter. Um, there is a dimension x right here, and in the drawing you can see, okay, it's a length. Okay, so from geometry, they figure out that here has to be perpendicular. So there is a length right here. So it's like a characteristic length kind of represent the shape of the tooth. So when the tooth is wider, then this angle changes a little bit. So this particular x length may be shorter or longer, depends on the shape of the tooth. So it's a parameter that could be representing how the tooth look like. And also there's a P. P is basically pitch. Okay. So for here, a pitch is like this. So you have a pitch circle, and let's say the arc length from here to here. This is pitch. So it's also another characteristic length to describe the shape of the tube. And it's being defined in such a way so that certain mathematical derivation can be properly simplified to a certain form, and which is good for stress analysis. And let's take a look at what happened. So under this way of doing the stress analysis, they no longer analyze the stress everywhere inside the geometry. They simplify it as a cantilever. So the drawing right here is representing how they view this a tooth in a different form, a much simpler form. So it's just treated like a cantilever, but this is being tilted by 90 degrees, being rotated. So this is like the root of the tooth, and you have a cantilever. So every tooth is like a cantilever. And you know when gear conjugate with each other, when two gears conjugate, sorry, poor drawing. So when the gear conjugate with each other, there will be certain force being applied from the other side to our side. So at certain low condition, there will be a force applied at the tip. So why do we study for this particular moment? Because at this moment, that's where the external force coming from the other side is going to generate the most stress for this particular tube. So for mechanical design, we care about the worst case. We don't need to study for some other condition where the force comes from the other side to here, but not applying at the tip. There will be some other moment the force comes at the middle, but that's the moment that doesn't generate the most stress. So we only care about the one that is the most extreme. That's why we only need to study for this particular configuration. And how much force is going to be applied from here is going to be related to the geometry of the tooth, and there will be this is like the pressure angle. Okay, so if you have two pitch circle and two pitch circle between two gears, and there is always a pitch angle, a pressure angle. So the force coming from the other side and passing through this particular straight line having a tilt angle. And this is how this model knows where the force comes from. And when they treat this tooth as a cantilever, they don't even care about this one, because this like a vertical force basically is following the radial direction. R represents radial, and T is represent transverse. They only care about the transverse load. Why? Because this one basically compressed, and you have a lot of material here. It doesn't bend the tooth. The tooth won't be breaking due to compression. It breaks due to bending. So for the force condition, they only care about the transverse. So that would be the WT right there. Okay. They only care about WT. So WT will be the load times the cosine pressure angle. Okay. And then L would be the length of the tooth T is like the width right here. So what does this part mean? That is the cross section of the cantilever. So for a tube, usually there's a thickness, and they usually call this thickness as face. So F represents the face width. So F is the face width. Okay. So that's why from here you have like F right here is like telling you how thick the tube is. So instead of studying this curvy geometry, they study that cantilever. Then you can easily formulate the stress equation. It's basically MC over I, and they start to plug in the moment of inertia I, and by changing the coefficient into this expression of x, they end up with some equation like this. Okay, so the stress equals to transverse load times the length of the tube divided by the width of the tube and also width over here squared. And it could be rewritten into this form by playing with the numbers. And over here you will see this value 2/3, right? And this is why when they define Lewis vector, they have this 2/3 right there. So some of the values can be eliminated later on. So at the end, they have this very simple equation at the end. So it's gonna be transverse load divided by the thickness times pitch times this Lewis vector. So at the bottom, it's like a force over area, but the area is being designed as a effective area in terms of the Lewis vector. So they can study for this. So once you can study for stress, so all you need to do is some kind of design equation. So for this particular one, stress has to be smaller than the yield strength. So let me show you. They basically want to do. Okay. They basically want to do this. Stress, yield strength. Yeah. That's basically what they are looking for. Once they know the stress level, okay, then it has to be smaller than the yield strength divided by safety factor. However, when they do this modeling, they didn't consider enough conditions. They realized this is too much simplified. And for different operating conditions or different choices of materials and different under different factors, this equation become inaccurate. So let me show you what's gonna happen at the end. They have so many correction factors. So like the book is gonna tell you, oh, there is a dynamic effect based on different speed of the gear. The stress needs to be multiplied a certain value. So this is one fact. So why do they know this? They must have done experiments and they realize you need to pre-multiply certain factors. Okay. Let me just go to the final form, just let you know how it's gonna look. So many vectors. Just give me 1 minute, I'll just show you here. This is what it looked like at the end. Basically, bending for the gear tube stress equals to, this is the transverse force, and then a lot of K. All the K's represent some coefficient. And the book tells you, okay, if you want to compute for this K, go to the book page certain number. Okay, and then this is the limit. The stress must be smaller than this value. And over here, SF is basically safety factor. Okay, and some other coefficients. So at the end, it's still the same equation, but with a bunch of K's. A bunch of K's, something like this. So those are corrected coefficients. So if you get the concept why gear design equation look like, then you are not afraid of it. You just need to know, oh, for gear 2, I need to multiply so many coefficients. But concept-wise, it's all about stress smaller than the stress limit divided by safety. Okay, that's how I relate static load model with a gear chapter. And that's it for today. And remember to do the attendance check. I will be traveling on Friday, so next week, either you see Dr. Patel or you see me online. Okay. That's it for today. Thank you.